Okay, so I'm going to do a brief demonstration of a problem. This is going to help you on problem number 5 of your second problem set. Um, in problem 5, you're asked to find the probability of finding a particle in the classically forbidden region for a harmonic oscillator in the v equals 1 state. So I'm going to show an example with the v equals 0 state. So in this particular problem, our task is to calculate the total probability of finding a ground state harmonic oscillator in the classically forbidden region. Okay, so that means what's the probability of finding the particle at an x position, either greater than positive x turning point or less than the negative classical turning point, right? So the probability of finding the particle at an x position greater than the turning point is just the integral from the turning point to infinity of the probability distribution dx. And the probability distribution, of course, right? The probability density is the square of the wave function. In the case of a harmonic oscillator, the wave function is real valued, so you don't have to worry about any complex conjugates in this formula. Okay, like we said in class, the classical turning point for a harmonic oscillator is given by this expression here. If you recall, we derived this expression by setting the energy of the particle, right, E sub v equal to the potential energy, right? That's where the classical turning point is, and then we solve for x. And so we're going to use this expression here in this integral. But it's actually going to be a little bit more convenient to do this integral in terms of dy instead of dx, where, y is equal to x over the alpha parameter. Alpha is this parameter that has dimensions of length, and it's given by the fourth root of h bar squared over the mass times the spring constant. Okay, and so the y value at the classical turning point is just the x value at the classical turning point divided by alpha. So if you take this expression here for the x value at the classical turning point, you can substitute in the expression for the energy of a vibrational energy level. Recall that's v plus a half times h bar omega. So we're going to substitute that in for E right here. And then that gets multiplied by 2 divided by k. And then we've converted y to x. So we have to divide by alpha. When you put alpha inside the square root, you have to take alpha squared. And next, what you can do to simplify this expression is plug in the expression for omega. Omega is equal to the square root of k over m. And you can also plug in the expression for alpha. Alpha is this expression here. And when you do that, there's going to be a whole lot of cancellation. You're going to see the factors of h bar, they all cancel. The factor of m cancels. And the spring constant k sub f in the numerator and denominator also cancel. And you're going to be left with the square root of 2v plus 1. Okay, but in this particular problem, we are working in the v equals 0 state. And so the y value at the classical turning point is just going to equal 1, right? The square root of 1 equals 1. Okay, so therefore, this integral that we want to do, if we make the substitution, right, substituting y for x, then dx is equal to alpha dy. And so when we substitute this expression here, we get a factor of alpha. Alpha is a constant, so it comes out of the integral. And at the x turning point, the value of y is equal to 1, which we just derived on the previous slide. Okay, so this is the integral that we want to do. If we plug in the expression for the wave function for the ground vibrational state, the Hermite polynomial for v equals 0 is just 1. So we don't have to worry about the Hermite polynomial, and we just get a normalization constant and not squared times the Gaussian function squared, right? And when we square the e minus y squared over 2 function, we just get e to the minus y squared. Okay, so this is the integral that we want to solve. We can plug in the values of these constants out front. So the expression for the normalization constant and naught was the square root of 1 over alpha times the square root of pi times 2 to the v. V is 0, so we get 2 to the 0 power times v factorial. But for v equals 0, we just get 0 factorial. Okay, and then if you note that 2 raised to the power of 0 is equal to 1, and 0 factorial by definition is also 1, right? A lot of people forget 0 factorial is equal to 1. That's the mathematical definition of 0 factorial. Okay, and so therefore the normalization constant is just this expression here. And so the normalization constant gets squared. So we're going to get 1 over alpha times the square root of pi. And there's going to be an alpha in the denominator that cancels with this alpha in the numerator. And finally, the expression that we have for the probability of finding the particle with a y value greater than 1, right? So with a classic, x greater than the x of the classical turning point is equal to this integral here. Okay. Yeah, and so unfortunately, this is an integral that does not have a closed form analytical expression. So this is the integral of a Gaussian function. If you integrate the Gaussian function from 0 to infinity, you will find a closed form expression in your textbook in the integral table. But if you go from an arbitrary value to infinity, there's not a closed form expression for that. So the integral of a Gaussian function is a special function called the error function, but there's no analytical expression for the error function. So this is something that you have to calculate numerically. Okay, so let's do that using a spreadsheet. And we're going to use the method of taking a rectangular integral like we talked about in the previous discussion section. So here I have a spreadsheet that I've prepared. I've plotted this thing that we need to integrate. So this is pi. So this is 1 over the square root of pi times the exponential of minus y squared. I'm calculating this function from over some finite range of y, but you basically want to choose a range of y that's enough so that the value of the function basically goes to 0. Okay, and then you don't actually have to literally integrate from 1 to infinity, right? Because if the function goes to 0, then you don't have to consider values of y that are greater than, in this case, about 3. Okay, so we want to calculate the probability of finding the particle at a value of y greater than 1. And that's going to correspond to the area under this portion of the curve, right, with y greater than 1. Okay, and so in order to calculate the rectangular integral, we can use the method that we used last time in class. So we're going to take the delta y interval, which in this case is 0.02, and we're going to multiply that by the sum of all of the calculated y values, right, which have an even x spacing between y equals 1 and the maximum value of y, right? And this is going to be a good approximation of the integral under this curve from y equals 1 to infinity. Okay, so I'm going to sum all the I'm going to sum all of the values of this function here from y equals 1 to y equals infinity, basically. So I'm going to scroll down. So here's y equals 1. So I'm going to take this value here, and I'm going to take the range from here, basically to the maximum value of y, close parentheses, enter, and I get the integral now. So it's about 0.08. So that means that about 8% of the probability distribution is located in this classically forbidden region over here. Okay, so to find the total probability of tunneling, we have to add the probability of being in this region here, this classically forbidden region on the right-hand side, plus the integral on the left-hand side. by symmetry, these integrals are going to have the same value. So you could just take 2 times this number. For the sake of demonstration, I can also just calculate the other integral. So the probability that y is less than -1 is found by taking the interval delta y, right, which is 0.02 in this case, times the sum of all of the values of the function from basically the minus infinity, right? In this case, we're just going to go to -3 because the function has already gone to 0 at that point for all intents and purposes. So I'm going to go from -3 to 1. For some reason, it's not wanting to scroll down. Oops. Okay, sorry, I went a little too far. Okay, my computer's not wanting to scroll right now, so I'll just do this manually. So I want to go from, or okay, I can click and drag. So I want to go until y reaches a value of -1. So that is right here. Okay, and then as expected, I get the same integral on the left-hand side that I got on the right-hand side. So the total probability of tunneling, I could call that P tunneling, is just found by adding together these two integrals. And you get about 0.16. So in other words, there's about, if you measure the x position of the particle or the y position of the particle, there's about a 16% chance of finding the particle in a classically forbidden region. So tunneling is not an effect that you can ignore when you talk about the behavior of molecules, because at room temperature, most molecules are in the vibrational ground state, right? So they're in the state that's described by this probability distribution here. And there's actually, a non-negligible probability of tunneling into the classically forbidden region. Okay, so good luck on your homework, and I will see you guys in class.